Okay, so in today's class, we'll go through uh, the process states. So when a process will be created and it is there in the secondary memory, so how we'll get that particular program from the secondary memory to the main memory, and what are the thing that will be take place, and what are the different states a process could be, that we'll see today. So because this is also one property of a process, because the property of a process is called context, and it is also called process control block. It is also called task control block. Mainly in different books, the attributes related to a process is called process control block or context. Okay. Now, in today's class, we'll see different states of a process. So there are different states. We'll go one by one. We'll see. The first state of the process is called new state. New state when the process is being created. So once a process is created, and at that particular time, we say it is a new state. Means a process is in new state. Then we have ready state. The process is waiting to assign a processor. Means process is waiting in the RAM and it is waiting for a processor to assign. At that particular time, we'll say it is a ready state. Then we have running state when the instructions inside the process will be executing in the CPU. That particular state, when a process will be there in that particular state, is called running state. Then we have waiting and block state, waiting or block state, when the process is waiting for some event to occur. So generally what will happen is process is ready to run, but what will happen, sometime it need some IO operations to perform. So generally what will happen is in the CPU, when instruction will be executed of a process, so sometime CPU will realize that a process required IO, some IO operations. So what it will do is the process will be sent back to a mode which is called waiting state or the block state, where a process will do their IO processing. Okay, IO related processing, input output related processing. Then once the process will be executing on all the instruction related to process will be executed, it will go to the terminated state or complete state when the process has finished its execution. Then we have two more states. One is called suspend ready state. The process suspended, which is waiting to be assigned to a process. What will happen is what is the suspend ready is when there is a process and there are, let's say, n number of processes can be accommodated in the RAM. Okay, and my system is a multi-processing system where where I can process multiple processes. But what will happen is, let's say the limit of my RAM, which is my main memory, is let's say 100 processes, and there are 100 processes at a time. And suddenly, a new process with a greater priority will come into the ready state. So, what will happen? There are some processes which are not that much of important, means the priority of those processes are less. So, those processes will put into the suspend ready state. Getting it? And we can accommodate more priority processes into the ready queue or into the main memory. So that's why this state is there, which is called suspend ready state. Then we have suspend waiting or suspend block state. When a process is waiting in the waiting state, and from that state we are suspending any process. So that particular process will be in a suspend waiting or suspend block state. Okay. So a process could be in any of these state. Okay, so if one process has been just now has been created, so that could be in any of these processes. So let's see one by one. New, when a process is in a new state, so what will happen? Where the process is right now, the process should be there in the secondary memory. Okay, will be there in the secondary memory. When process is in the ready state, means where will be the process? Process will be in a main memory. Main memory. When process instructions are executing, then also that process is in the main memory, but executing into the CPU. Means some of the instructions of the process is executing in the CPU. So actually it is there in the main memory. Waiting or block state. So waiting or block state will be occur to a process at that particular time. The process could be in a main memory, or sometime it will be in a secondary memory. Terminated or completed means the process will be get out from the main memory and given to the secondary memory. Suspended ready means a process was in the main memory in a ready state, but after some time what will happen? It will go into the suspend state, and other more priority process will come and take its place. So it will go to the secondary memory. Suspend waiting or suspend block. So that is taken from the waiting state and given to the secondary memory. So this is how it the different position of a process at any given state. Okay. In a multi-programming operating system, we are using two type of processing. Means we can do two type of processing in a multi-programming. One with preemption and second without preemption. Okay. I'll tell you one by one what are those with preemption and without preemption. Let's see. Now what happened when any process is ready to run, it will be accommodated in the main memory. Okay. Let's say in the main memory we have process 1, process 2, process 3, process 4, and process 5. This is ready queue. Okay. Ready queue means these processes are ready to run. There is a CPU scheduler. This CPU scheduler is the responsibility of the CPU scheduler is to pick up any of the program which is there in the ready state and put into the CPU. So scheduler will decide that which particular process is going to change its state and going to the CPU and being in a running state. Okay. Now, if we are using, these are all multi-programming, right? Multi-programming is multiple program is ready to run. Okay. Now, if we'll use, there are two techniques, right? With preemption and without preemption. Let's talk about without preemption first. Now, what happened in the without preemption multi-programming system? That there will be no preemption algorithm. Means if a program is, if let's say P4 is going to the CPU, so P4 will perform all its instruction, means it will run all instruction and go out as a completion and go out in a state called termination, or it is also called complete state. When it is completed, what it is completed, it's all instruction will be executed. At that particular time, it will go to the terminated state. Now what happened when we are using with preemption? In the with preemption type of multi-programming system, the CPU scheduler will be scheduling a program for a smaller period of time. Okay. So what will happen on that a program, let's say P4 is there. P4 is associated with many instruction, let's say I0, I1, I2, I3. So CPU, let's say it is using some time sharing scheduling algorithm, which is called round robin. So what will happen is CPU will allot, let's say 2 milliseconds to all the processes. So in that way, what will happen is P4 will be allotted the CPU. It will perform its operation in 2 milliseconds. Let's say it has operated up to I0 and I2. And after that, P4 will be preempted and back to the ready state again. And after that, what will happen is, that is called preemption. And after that, what will happen in next program is going to allot in the CPU, right? So if this type of scheduling is going on, that is called preemptive scheduling. Okay. So we have two type of scheduling of CPU. One is called preemptive, another is called non-preemptive. Preemptive means there is the chance that the process which is running at a time in the CPU will be forcefully take out from the CPU and put it into the ready state, and other program with higher priority or next time slot can be occupied into the CPU. So for the multi-programming to be executed or to be done, the CPU scheduler will take care of it and it will do the preemption operation. So for the preemption, this is one criteria, that the time sharing. The other criteria of the preemption is priority. So there may be the chance that a process with the higher priority came into the ready queue or into the ready state, and this program want the CPU resource right now. So what will happen? The CPU scheduler will stop its programming of the existing process which is inside the CPU, take it out, put it into the ready state, and give the chance of the higher priority process to execute into the CPU. Getting it? So this is how we can implement the scheduling with preemption. So this concept is required to understand different states of a process. Okay. Now, what are the processes? Let's do a revision, quick revision. So the states are new when a process is created, just now created. Ready means the process is waiting for a processor. Running means the instruction of the process is running inside the CPU. Waiting or block, when a processor required any IO operation to perform, it will be in a waiting state or block state. Terminate or complete, when a process will be complete its execution or finish its execution, it will go into the terminated state or completed state. Then we have suspend ready. Suspend ready means maybe there is a chance that the higher priority process will be there, is looking for the ready queue, and ready queue is not free at that particular time, or there is a chance that process is coming which has the higher priority than the existing process, and that process is in the waiting state. So that process will be given a chance to go to the suspend waiting state. Okay. Here we have a simple state transition diagram, or you can say process state diagram for a process. So first of all, when a process is created, it will be in a new state. In a new state means it is there in the secondary memory, not in the main memory. So in the secondary memory it is there. Then from the secondary memory, it will be coming into the main memory, which is in the ready queue. So it is in the main memory, which is admitted into the ready queue. And from the ready queue, it will be scheduled to the CPU in a running state. Okay. After running that particular process, it will go to the terminate state. And if, let's say, some interrupts can be occur due to some problems, like higher priority process has come into the ready queue, or let's say some sort of preemption algorithm we have used. So for that we need some sort of interruption. So on that, what will happen is the process will go to the ready state, because it is not finished. It will go to the ready state again, and another process will be given to the CPU for the running purpose. Or let's say if a process is running at a time and suddenly it requires some IO request or some event, it is waiting for that. So it will come into the waiting state. And once this IO has been completed for the process, it will again go to the ready state. Okay. So I think this you might have clear these 5 states. So 5 states are clear to all of you. I think we have new means just now a process is created. Ready means it is coming into the main memory. So there are many processes are in the ready state. Then from the ready state, the scheduler will decide which particular process has to go to the running state. Then a process will go to the running state. From the running state, after completion, it will go to the terminate state. If it is not completed, it requires some IO, it will go to the waiting state. And from the waiting state, once the IO will be completed, it will go to the ready state again. From the running state, if some problem occur related to, I told you just now, we have 2 problem can occur if any higher priority ready process is coming. So we have to forcefully take out the processor and put it into the ready queue, or there is a time sharing if we are doing time sharing scheduling algorithm. In that, if time is finished, then also the process has to be take it out and put into the ready queue. Okay. Let's draw the complete diagram of the process states and try to understand it fully, because here we haven't added 2 more state, that is suspended ready and suspended waiting or suspended block. Okay, let's see this, that how is actually works and what are the different components that will come here. So when a process is created, it will go to the state which is called new. So a process will come into the new state when it will be created. A process is created, it will be in a new state. After the new state, it will go to the ready state. When it will go to the ready state, once the process will be ready for execution. At that particular time, the process can go into the ready state. Now, after that, if a process is there in the ready state, then what will happen? Then it can go to the running state. And who will take the process to the running state? There is a scheduler or dispatcher. Okay. Scheduler or dispatcher will take the process from the ready queue to the running state. In the running state, once it will finish or it will complete, it will go to the complete state or terminate state. After completion. Okay, after completion, it will go to the terminate state. Let's say if a process is running into the CPU and suddenly it required some IO, then it will go into the waiting state. Or it is also called block state. And from the block state, it will be resumed to the ready state when the IO completes. When the IO operation related to the process will be completed in the waiting state, it will go into the ready state again. Let's say a program is not required IO, but due to higher priority process, or due to time quantum allotted to a process will be expired, then also the process will go from the running state to the ready state. Okay. Now after that, if some process is waiting here in the waiting state, and assume that another process with the higher priority come into the RAM, and there is no room in the RAM, so what will happen is, from the waiting state, we will choose some of the process and we will do it suspend. When we do suspend, it will go into the suspended state. And it is suspended because it is coming from the waiting, so it will be suspended waiting. This is a suspended waiting state. From here, it can come into the waiting state when we resume it. Means, let's say the main memory is right now free, means you can come right now into the main memory. A process can go from the ready also, to the suspended state. That is called suspended ready, because it is there in the ready state and you have taken from the ready state to the suspended due to what? Some as I told you, some higher priority process come into the, so it will be suspended. And it can be resumed whenever there is a place for this particular process. If some process is there in the suspended waiting, and at that particular state, let's say that process has finished its IO, then also it can join this particular state, which is called suspended ready. So it will be the process completes its IO in process completes its IO. Okay. In which particular state? In suspended waiting state. Then also it can join the suspended ready state. So I think that particular diagram, which is called your process state diagram, is clear to all of you. So once a program is created, it will be in a new. From the new, whenever it is ready, it will come into the ready state. From the ready, the scheduler or dispatcher will take it to the running state. So the preemption has been done here. After the preemption, or the time content will be over, the running from the running state, a process can go to the ready state. Or if some process is waiting in the waiting state and it has been suspended due to other higher priority process which want to accommodate into the main memory, so it has to be suspended and it will be resumed once it will once there is a space for the main memory. And from the ready state also, process can be in a suspended ready state if any higher priority process comes into the main memory, or it can be resumed again once there is a free memory in the main memory. From the suspended waiting also, because so from the suspended waiting also, a process can come into the suspended ready state by process completes its IO while the process is in a suspended waiting. So let me tell you what are the different memory that we are in. So as we have discussed, here it is secondary memory. Here it is main memory. We are running in the CPU, but still your process is there in the main memory. Terminated means it is in the secondary memory. Waiting means it is in the main memory. Suspended waiting means it should be in a secondary memory, because we have suspended due to one reason, because the RAM does not have the space to accommodate new one. That's why we have suspended. And here suspended ready is also in the secondary memory. So you see all the memory we have defined. Now the question came from the suspended waiting, how a process can go to the suspended ready. The reason is, for the IO operation, we doesn't need any sort of CPU or any sort of main memory there. So from the secondary memory also, a process can complete its IO operations and can go to the suspended ready state, which is again there in the secondary memory. Okay. All the processes required some sort of scheduler. So there are three types of scheduler that will be used. So the first scheduler is called long-term scheduler. What is that long-term scheduler is? The long-term scheduler will take care of the scheduling from the new state to the ready state. Means what are the process that I'll take from the new state to the ready state, that will be taken care by the long-term scheduler. Means a process will be taken from the new state to the ready state by long-term scheduler. Why we say it is a long-term scheduler? Because here there are long-term processing will be done and will be decided that which particular process has to be chosen, because here in the ready queue we have 100 or 200 number of processes, depend upon the main memory and the operating system, how much it can accommodate. So that that particular decision is a long-term decision. That's why the long-term scheduler has been work here. Now from the ready state, if we have to take the process to the running state, that particular thing will be done by the short-term scheduler. What is that short-term scheduler? That short-term scheduler will choose that which particular process right now I will take to the CPU. That will be decided by the short-term scheduler. And after the decision will taken that this particular process has to be taken, after that the dispatcher will take the control and dispatcher will take the CPU, the process to the CPU. And from the CPU also, if a process has to go through the ready state, it will be again done by the dispatcher, will take the process which is just now not finished yet to the ready queue or the ready state. Now there is third scheduler which is called medium term scheduler. That medium term scheduler will taken care from the transition of running to the waiting and waiting to the ready. Okay, so that particular thing will be taken care by the medium term scheduler. So there are different type of schedulers that will be useful here, and to take the process from one state to another state. Okay, I think this particular concept is clear to all of you. This is very important and generally come into your examination. So different states are there, and why we are using for all the states of the process, so that we can see that which particular state will be there for a particular process. Means a process could be there in any of these states, and the scheduling will be done like long term, short term, medium term scheduling. So the process scheduling will be done. Now there are some more reason why we do all these transition. The reason is multi-programming operating system. To make a multi-programming operating system, we need all these transition from the CPU to the main memory, from the from the CPU or running state to the ready state, or ready state to the running state. All those things we have to do. The second reason is CPU utilization. We have to utilize CPU as much as possible. Okay, if we have a good CPU, and the CPU has a very good power, and if we are not utilizing it, so it is of no use. So to maximize the CPU utilization, we do these type of scheduling. Quickly switch process into the CPU for time sharing. So as I told you, multi-programming system is nothing but time sharing operating system, where each and every process will given different time slice or different time quantum. So in that particular time quantum, let's say 2 millisecond has been allotted to program 1. Again 2 millisecond will be allotted to program 2. In that way, what will happen is 2 seconds will be allotted to program 1 and will execute its instruction for 2 millisecond. Again it will come out and be in the ready queue. P2 will come into the CPU, again 2 seconds, it will come into this ready queue, then P3 will come. In that way, the round robin fashion, in that way, we can implement multi-programming operating system. The process scheduler select among available processes for next execution on CPU. As I told you that if any process is in the ready state, from the ready state to the running state, who will decide? The CPU scheduler will decide. The CPU scheduler is nothing but short-term scheduler, and that will be decided by the scheduler, and it will be dispatched by the dispatcher from ready queue to the running, or from ready state to the running state. So we have to maintain different queues, like there are job queue, there are ready queue, and there are device queue. So what is job queue? set of all processes in the system means new. The new state, there is a job queue. Ready queue means all the set of all the processes are residing in the main memory and ready and waiting for the execution. We need ready queue. Device queue means if some process is waiting for the IO operation or IO device for the execution, it will be in a device queue. Processes migrate among the various queue. So we have different queues, right? So as I told you, we have different queue like ready queue. Then we have waiting, that is a waiting queue. So there are different queue. This is a queue. This is a queue here. This is also a queue here. This is also a queue here. So we have different queues available, and all these queue have different process inside the queue. About the scheduler, I told you there are some schedulers. Like first we have seen long-term scheduler. Long-term will be responsible for taking the data, taking the process from running ready state, new state to the ready state. It will select which process should be brought into the ready queue. Long-term scheduler is invoked infrequently. Second, minutes may be slow. So that's why it is a long-term decision has to be taken. It is very slow. Long-term scheduler controls the degree of multiprogramming. Means how much a program will be there in the ready queue. It will be decided by the long-term scheduler. Then we have a short-term scheduler. Means from the ready queue to the running state, which particular process has to go. So that will be decided by the short-term scheduler. That is also called dispatcher or CPU scheduler. So it will select which process should be executed next and allotted the CPU. Sometimes the only dispatcher in the system, short-term scheduler is invoked frequently in a millisecond, or it may be more faster. Then we have medium-term scheduler. Can be added if the degree of multiprogramming need to decrease. Remove processes from memory, store on the disk, bring back in from disk to the continuous execution, that is called swapping. Select which process should brought into the suspend ready queue and suspend waiting. So the medium term scheduler will work here. So I told you about the waiting state. Here also it will work. So from this waiting from the main memory, if I need to take any process to the secondary memory, the medium term scheduler will take care of it. That process is also called swap or swapping. Okay, that process is also called swapping. It is a responsibility of middle term scheduler to manage the main memory, and it will decide that if any high priority process come into the main memory, then lower priority process has to be suspended from main memory to the secondary memory. As well as if we are taking from the running state to the waiting state or waiting state to the ready state, that is also decided by the medium term scheduler. So we have seen different type of schedulers now. Okay. Okay. And there is a concept of context switching. Yesterday I told you that the process attribute which is also called PCB, process control block, or task control block, or context. So these are different names of process attributes. So this PCB is required to switch from one to another due to process switching done by the short-term scheduler, and that process is called context switching. So when a process will be switched from the CPU and to the CPU, we need to do context switching. Okay. When CPU switches to another process, the system must save the state of the older process, and the older saves state of the new process via the context switching. So the state has to be saved, that which state it is, what are the different CPU register value is, what is the program counter is. So all these things will be saved. That is called states of that particular process. So the process state has to be saved and new process has to be loaded, and that particular new process state also has to be saved somewhere. That particular process is called context switching. Context of a process represented in the PCB, process control block, we have seen, right? So the context switching time is a overhead. Means at that particular time, CPU is not doing any useful work. No useful work will be done by the CPU at the time of context switching. The more complex the operating system and the PCB, the longer context switching. So there are different new operating systems where this process control block size has to be reduced and operating system program has to be less complex. If we are doing that, the context switching will not take longer time. So time dependent on hardware support. Some hardware provide multiple set of registers per CPU, multiple context loaded at once. So if we have multiple register in the CPU, so we doesn't have to save the CPU registers or the general purpose register, right, of the CPU. So here also we can save the time for the context switching. So context switching means when CPU switches from one process to another process, we have to save the old process state and we have to save the new process state. That process is called context switching, or that particular part is called context switching.